In this lesson, we're going to talk about derivatives of equations that have a natural log function included. So if you will set up your paper for Cornell Notes and get your essential question written down, and then proceed to the next slide. Okay, so there are a few things that you need to remember about the natural log function. And the graph is shown here, and you will notice that the graph has an x-intercept at the point 1, 0. It is the parent function graph y equals ln of x. It has an asymptote, a vertical asymptote at the y-axis. So the domain is from 0 to infinity, but the range is negative infinity to positive infinity. So it does keep rising, not very rapidly, but it does keep rising. This function is continuous, increasing, and one-to-one, and the graph is also concave down on its entire domain. You also, in Pre-Cal and Algebra 2, learned some properties of logs that are listed here, and these are things that you're going to need to be able to work with as we are taking derivatives of natural log functions. So if you will pause, write down these properties, hopefully they are familiar, and then start the video when you have gotten them into your notes. Okay, so the calculus part starts here. Whenever we're taking the derivative of an ln, okay, the derivative, if it's just ln of x, is equal to 1 over x. And this says x greater than 0 because, remember, ln of x is only defined when x is greater than 0. So the derivative of ln x equals 1 over x. This will become a flashcard when you get to class. Okay, now if it's not just an x, as most of these functions will not be, so if you have ln of u representing any other function, we're still going to have 1 over u in our answer, but then this becomes a chain rule problem. We do have to find the derivative of whatever that function was. Okay, so 1 over u times du dx, because we're taking the derivative with respect to x. So anytime there's any function in there that's not just an x by itself, you're going to use a chain rule. Another way to write that is to say u prime over u. That's the derivative of that inside function over the original function. And in number 3, you'll notice that if your function is in absolute values, it does not change your derivative rule. Still the derivative divided by the original function. Okay, so let's look at a few examples. Okay, so in the first one, our u would be the x squared plus 2. So the derivative of ln of u is du, or u prime over u. Okay, so I need the derivative of that function. Derivative of x squared plus 2 is 2x. Okay, the original function, the u for the bottom, is what we started with, x squared plus 2. If it reduces, you may reduce it. This one does, there's not really anything you can do to simplify it. So your derivative, again, u prime over u. Okay, now in part B, there is something you can do to make this problem easier. You can start taking the derivative just like it looks, but then you're going to end up using a chain rule with a fractional power when you're finding the derivative for the numerator. So one thing that you can do to make this easier is to use your properties. We need to do a rewrite on this using our properties. So if you'll recall, there is a property for natural logs, and I'm going to write this with an exponent, so x squared minus 9 to the 1/2 instead of square root of x squared minus 9. There is a property for natural logs that says if you have an exponent, that you can bring that down in front and multiply it times the natural log of your argument. So I'm going to rewrite this to say y equals 1/2 times the ln of x squared minus 9. A whole lot easier to take the derivative now than it was before we did the rewrite. Okay, so since 1/2 is a constant, I'm going to use my constant multiple rule. and I'm just going to keep the 1/2 and multiply it times the derivative of ln of x squared minus 9. And again, remember it's u prime over u, with our u being this x squared minus 9. So I need the derivative of that equation, or that function, x squared minus 9, which would be 2x, divided by the original function, x squared minus 9. Okay. And I can simplify this problem a little bit because I've got the 1/2 times the 2x over x squared minus 9. So the 1/2 and the 2 can cancel each other out and simply leave me with x over x squared minus 9. Okay. Now, let's look at a couple other functions. Okay. So in part C, you've got the ln of the ln of x. You still want to think about this. What is my u? I'm taking the derivative of an ln, and this inside function is the ln of x. Okay, so I'm going to let this be my u. Okay, so the derivative of the outside, the ln part, is u prime over u. Okay, well, u prime, the derivative of ln x, is 1 over x. And then I put that over my original function, which was ln of x. But I don't want to leave this as a complex fraction. So remember, this could be written as ln of x over 1. And to take care of the complex fraction, I'm going to multiply by the reciprocal of that denominator. So I would end up, if I put that all together in one answer, as 1 over x times the ln of x. So it looked weird at the beginning with the two ln's, but still, you just want to think about what is my inside function. Okay, now part D again is another one where you're going to want to use your properties to do a little bit of a rewrite before you start taking the derivative. So I'm going to make that y equals, okay, so on the top I've got 3 times x. I can break that up or I can leave it like it is. Okay, so I'm going to do this as if it's multiplication. Remember, the property is that you split it up with addition. So ln of 3 plus the ln of x. And then if you've got something that's divided, your property says that you subtract the ln. So minus the ln of x minus 2. So we did a rewrite on this. And now we're going to take the derivative for each part separately. Okay, so the ln of 3 is a constant. When I take the derivative of a constant, I get 0. The derivative of ln x is simply 1 over x. That's one that you're going to memorize. And then for ln of x minus 2, I'm going to have to use my ln of u formula, which is u prime over u. The derivative of x minus 2 is 1. And then my original function, my original u, was x minus 2. Right, now, one thing that you can do to this, if it's on a multiple choice section of the test, you're going to have to get a common denominator. So I'm going to go ahead and keep simplifying here. So our common denominator would be x times x minus 2. So the first fraction needs to be multiplied by x minus 2. The second fraction times x, numerator, denominator, which would give us 1 times x minus 2 is x minus 2. Minus x over our common denominator. I can simplify this a little bit by canceling out the x's. X minus x would cancel each other out. So my final answer will be negative 2 over x times x minus 2. Be sure that you write question marks beside anything that you're not sure about. Okay, now anything that we've been asked to do with derivatives before, we can be asked with derivatives that involve ln's. So let's look at this next example. Find the slope of the tangent line. Keyword, slope of the tangent line. And whenever you see slope of the tangent line, the first thing you should be thinking is, I need the derivative. Okay, So derivative gives me the slope of the tangent line. And my function, the only difference between this and what we've done previously is that now my function has an ln. So we're going to find the derivative. We're going to say y equals, okay, my function is x to the 3/2, and I can actually rewrite this again. Using my properties, I can make that y equals 3/2 times ln of x, because the exponents can come to the front and multiply. Okay, so 3/2 times the derivative of ln of x, which would be 1 over x, gives me a derivative of 3 over 2x. And they've asked us to find the slope of the tangent line at the point 1, 0. So now we're going to take our point and plug into our derivative. Okay, so y prime would equal 3 over 2 times 1, or 3/2. And although the question does not ask us for this, let's write the equation of the tangent line. And remember, the equation of the tangent line, you're going to use your point-slope form. So y minus y1 equals the slope times x minus x1. The point given to us was 1, 0. So I would have y minus 0, or just y. My slope is what I found after I took the derivative and plugged in the point. And then x minus x1 would be 1. And I can leave it that way, or I can distribute. So anything that we were asked to do before with derivatives, we will be asked to do with the ln derivatives. Okay, one last example. Implicit differentiation. Implicit means that we've got two variables, we've got x's and y's in the same problem. We're taking the derivative, notice, dy dx with respect to x. So anytime we take a derivative of a y, we have to put in the dy dx. It's like a chain rule. So derivative of x squared is 2x. 2 ln y, the 2 will multiply times the derivative of ln y. Okay, and the derivative would be 1 over y times, again, since it's a y, we need the dy dx. It's like a chain rule. And then the derivative of 3y squared would be 6y dy dx. And the derivative of 8, since it's a constant, would be 0. Okay, now all the terms that have dy dx we're going to collect together on the left side. We're going to move the 2x to the other side. So I will have a negative 2 over y if I multiply those together times dy dx plus 6y dy dx equals negative 2x. If you'll factor out your dy dx, okay, then you will end up with negative 2 over y plus 6y. And then the last step we have to take is to divide. So we would have dy over dx equals negative 2x divided by negative 2 over y plus 6y. Now, it's a complex fraction, so again, there is some algebra that you can do on this and simplify, get a common denominator, and take care of the complex fraction. And when you do all the simplification, which I want you to do on your paper, this is the answer you should get to. If you can't get that answer, put a question mark and ask in class. Okay, so derivative of ln x is 1 over x. If it's not just an x, the derivative will be u prime divided by u, the derivative of the function divided by the original function.